This is the second part of the normal distribution. Don't need the date. Most data for a normal distribution will lie within 3 standard deviations of the mean. An example is shown here. This will be helpful when you're asked to draw a sketch. Given the mean and standard deviation, you can plot the highest point, which is the mean, and then the outer limits, the lower limit, mu minus 3 times the standard deviation, and then the upper limit, mu plus 3 times the standard deviation, just to give you a general idea of your sketch. Since very few real-life situations are distributed like the standard normal distribution, with a mean of 0 and a standard deviation of 1, but you can transform any normal distribution, x n mu sigma squared, to standard normal distribution, because all normal distributions have the same basic shape, but are just shifts in location and spread. So if you think back to 3UW, you would have done transformations of function. Any other normal distribution is really like a horizontal shift of the standard normal distribution, or the parent normal distribution. So to transform any given value of x, so that's the position on the x-axis of a normal distribution represented by x n mu sigma squared, to its equivalent z value, you can use the formula z equals x minus mu over sigma. So this is like you are taking the current position and shifting it so that the graph lies on a standard normal distribution. The random variable x is represented by the normal distribution with a mean of 10, and then variance, standard deviation of 2. What we're looking for is finding the probability that x is between 9.1 and 10.3. So we know that it's normally distributed, but we want to be able to standardize this. So to shift it so that the area under the graph is the same, but so that we can use our easier standard normal distribution. So what we're going to do is find our left limit. So we're going to shift our left limit first. We're going to take our x variable, take away mu, and then divide by sigma. When you do this, you get about 0.45. And then we're going to shift our higher limit, or our right limit. So we're going to do the same thing. Take away mu, divide by the standard deviation. This gives you 0.15. Now we have a new situation. We're now looking for the normalized probability between minus 0.45 and 0.15. So we can use, let's do this. So we're just looking for an answer. We can use the normal function on our graphing calculator, inputting our lower limit and our higher limit, and then our mean and standard deviation, which gives you approximately 0.233, or about a 23% chance. This is an example of one that you can also do without standardizing, because you know the mean and standard deviation. But it's just showing you how to standardize one. So if you didn't know one of the variables, that you would still be able to find the probability by shifting it to something that you do know. So let's look at our next example. This is more of a word problem type, great exam style question. Eggs that are laid by a chicken are known to have the mass normally distributed, so that should be the first thing that you think about. They have the mean of 55 grams and standard deviation 2.5 grams. What's the probability that an egg weighs more than 59 grams? So let's say W is our random variable. So let W represent the mass. Okay, so we've got our normal distribution would be N, 55, and 2.5 squared. Okay. These ones you could do with standardizing as we did in the first example, but you don't have to. Okay, we can do it. We know both of the pieces, so we can just use our regular normal CDF and plug in our endpoints. If you were to standardize with the new endpoints and mean and standard deviation, you would get the same answer. So this is our, sort of an aside, this is our normal distribution here, and we're looking for the probability that our mass is greater than 59. So on our graphing calculator, we would use normal CDF, and we're looking for greater than. So our lower limit is 59, and our right-hand limit is just a really big positive number. Then we've got our mean, standard deviation. Things are wonderful. You put that into your calculator. And let's see what we get here. So we've got second VARs to get to distribution. Scroll down to normal CDF. And then we've got 59, 9 times 10 to the 99, 55, and 2.5, which should give you approximately 0.0548. Let's look at the next example. So we're going the other way this time. So now we're looking for the probability that an egg is smaller than 53 grams. So here again, we can use our graphing calculator. Normal CDF. This time, our lower limit or our left limit is just going to be a really big negative number. Then we're going to put our right-hand limit. Then our mean and our standard deviation. And that should give you about 0.212. Last one is that we're looking for the probability that an egg is between 52 and 54. And so again, we can use normal CDF. So remember the calculator notation, you do not have to write down. It is not part of your solution, but I'm writing it here so that you have a reference if you're working on the practice questions. So again, normal CDF, we've got our left limit, our right limit, mean and standard deviation should give you about 0.230. Okay. Let's, just for fun, why don't we standardize this one, and then we can double check that we are actually going to get the same answer. So our lower limit is going to be our x value. Take away our mean, divide by the standard deviation, 52 should give us minus 1.2. Then we're going to standardize our right-hand limit. So we've got 54 minus 55 over 2.5. This is just using the formula from example 1. Okay. Here, we've got minus 0.4. So now, really what we're looking for is the probability that our new standardized variable z is between minus 1.2 and minus 0.4. So again, we can use our GDC, same distribution function, but instead we have new limits, and then we've got our original, our standard normal mean and standard deviation. So now when we do this, we should get the same answer. 0.401. Okay, which again gives you about 0.230. Standardizing is useful if you're missing one of those quantities. In this case, as in our first example, we know the mean and standard deviation for the distribution that we're studying, which makes it straightforward enough just to use normal CDF as is. If we didn't know the mean or standard deviation, then the question would be a little bit trickier, but we would be able to standardize it and to solve it.